This first homework problem from the book that I want to talk about is more conceptual and a little bit squirrely. It kind of uses some definitions and a lot of words, so let's kind of take the opportunity to unpack it. In this problem, each quotation is a statement about a quantity of something changing over time. That's what calculus is all about. Things changing over time because derivative is rate of change. And now we have a second derivative, which is how the derivative changes. Okay? So if f represents some quantity at time t, for each quotation, I want you to tell me what f represents and whether the first and second derivatives are positive or negative. So for letter A, unemployment rose again, but the rate of increase is smaller than last month. So we need to say, what does f represent? And are the first and second derivatives positive or negative? What should f represent here? Unemployment. F of t is unemployment at time t. Is f prime positive or negative? Is the second derivative positive or negative? Well, it's unemployment rose. Unemployment is rising. F is rising. F is increasing. What does that tell us about f prime? That tells us that f prime is positive. Now, here's the thing, is how is the derivative changing? The rate of increase is smaller than it used to be. The derivative is smaller than it used to be. F prime is smaller than before. That means f prime is decreasing. That was one of our definitions of concavity. It's concave down. The second derivative must be negative. So that's the thought process for the second derivative. Rate of increase is smaller than last month. That means, well, the rate of increase is f prime. So f prime is smaller than it used to be. If f prime is smaller than it used to be, that means f prime is decreasing. It means it's going down. F prime decreasing is our definition of concave down. And concave down, another way of thinking about that is having a negative second derivative. We can combine all of this stuff. It's increasing at a decreasing rate. If we wanted to draw a picture, this is what f looks like. Unemployment is rising, but it's rising more slowly than it used to. Positive first derivative because it's going up. Negative second derivative, concave down. I'll do one more of these. I won't do letter C. Our profits declined again, but at a slower rate than last month. So here F will be our profits. Our profits are declining. Our profits are decreasing. So that tells us our first derivative must be negative. That's the definition of a decreasing function. And the rate is slower than last month. This one's a trick question. Let's look at the picture. We're going down, but we're going down less than we were before. Think about being in your car and driving in reverse. Maybe this isn't helpful, but if you're in your car and you're driving in reverse and you slow down, you put on the brake, your acceleration is actually positive because your velocity is technically increasing, even though your speed is decreasing. That might not be helpful, actually. That's another way of looking at it. So again, f prime is actually bigger than it used to be. Okay? It's less negative than before. Okay? Maybe I should do letter C. This one's kind of confusing. It's less negative than before, right? We started off having a big negative slope, and now we have a less negative slope. This is also concave up, right? Happy face. Concave up. So it has a positive second derivative. B is definitely trickier than A. And then looking at letter C, population is still rising at a faster rate. So F is the population. Rising at a faster rate means it's going up and it's getting steeper. So very quickly, that tells us that F prime positive and it's concave up. That was a positive second derivative. That's how we tie everything together here. Let me know if you have questions about this one, especially letter B. It's definitely the most confusing. For letter B, I think it's easiest to start with the picture. From the picture, it's easier to see that we have concave up. All right, I like this problem too. I thought it'd be a great problem to include on the homework, so I wanted to do it, show you kind of what I'm looking for. Fill in the table with positive, negative, or 0. So let's look at this point to start off with. The function value, and again, this is maybe a good opportunity to show this, right? F, that's the y value. F prime, that's the slope. F double prime, that's the concavity. This might be the single best way to approach this problem. And it's good because this is really what the problem is trying to get you to connect. It's good practice for saying, okay, we have 3 different functions now. We're only looking at one function. This is the y value function. This is F. But these are our 3 functions that we really care about. So the y value at this black point is positive y value. The slope is also positive, right? We're increasing from left to right. If we draw a tangent line, it has positive slope. From left to right, as we go through this point, we're going up. Does it look like concave up or concave down? Well, in this whole section, right? This whole section curves this way. It opens down. It's concave down. And then we go through the next couple points. All right, we look at the second point. Still has a positive function value. I'm going to do all the points at once now. All of these points have positive function values, right? Those ones are maybe less interesting. Let's look at their slopes. Well, the function's decreasing here. There's a negative tangent line. Function's flat here. Tangent line 0. Function's increasing here. Positive. Now the derivatives, that's where things get a little harder. Would you say this point concave up or concave down, or kind of hard to tell? It looks like it's curving though, right? It looks like it's curving, and if I had to guess, I'd say it's kind of curving. You know, it's kind of curving like this. So I'd say both of these points are kind of concave up. Which means they have a positive second derivative. But look what's happening around this point when x is 3. Look at what the function does. The function's literally a straight line right here. We haven't talked about concavity of straight lines yet. So now let's not think of this as concavity anymore. It definitely is, but we didn't talk about concavity of straight lines, so that doesn't help us. Think of f prime, right? It's concavity, sure, but it's also how f prime is changing. This said f prime was getting smaller, f prime was getting bigger, f prime was getting bigger. How is the slope changing on this line? Well, that's the thing about lines. They have the same slope everywhere. The slope is not changing at all. The slope is not changing at all. It's 0. It's neither concave up nor concave down. All right. We're going to use this definition for that last one. They're both equivalent. And that's another great way of doing this problem. Another great reason to do it. Let me know if you have questions about that one. And now we want to find the first and second derivative of 21. Because I told you the hardest part of this section probably will just be taking derivatives. And I wanted to give you a messier one to follow along with. So if we do some messy stuff, what does that look like? Well, we're going to have to use the chain rule, right? We have a function inside of another function. So f, in terms of u is the inside function. So what is f in terms of u? Well, it's just the square root of u. And I said that u is x squared plus 6x minus 1. So remember that the chain rule said that the derivative of f with respect to x, and that's what we want, right? This is f prime. The derivative of f with respect to x is the derivative of f with respect to u times the derivative of u with respect to x. You can remember that by thinking of cancellation. These aren't actually fractions. These are derivatives, but we can think of them similarly. So the derivative of this function, how did we do that? Well, let's go off to the side. Remember, the square root of u can be written as a fractional exponent. So we can just use the power rule when we're taking the derivative. Bring down the exponent and subtract 1 from the exponent. Normally, we rewrite this now. We clean it up. We put it back as a square root. But I'm not going to put this back as a square root because we have more derivatives coming. And it's easiest to take a derivative when we have it in this form. So let's leave it as 1/2 u to the negative 1/2. Multiply by the derivative of u with respect to x. That one's easier. 2x plus 6. We're just using the power rule. So this is f prime that we found. We need to put everything in terms of x. We get 1/2 times u to the negative 1/2 times this. We're not done. But we do have the first derivative, so that's great. Now we get to take the derivative of this, which looks pretty awful, going to be honest. Again, for like a quiz or something like that, I'm not going to actually have you take the derivative of something this messy, but I do want to show you what it looks like. And it's good to be able to practice on the homework assignments. But in reality, this is not something I will give you on for an in-class activity. Okay, so how do we take the derivative of this? We break it down into small steps. So we need the derivative of this. Well, we have to use the product rule. Okay, let's have this be our first function and this be our second function. We usually call it f and g. I don't want to do that though because we already have an f. We can call it, I don't know, we can call it h and g if you want. So we know that the second derivative is the derivative of the first function times the second plus the first function times the derivative of the second function. All we need to do is find what h prime is and what g prime is, and then we just plug it in. It'll be messy, but not too bad other than that. So h is 1/2 times x squared plus 6x minus 1 to the negative 1/2. We have to use the chain rule. So we have this is our inside function. So h of u is just 1/2 of u to the negative 1/2. And we said u was the same u as before, x squared plus 6x minus 1. The derivative of h with respect to x, which is what we want, is the derivative of h with respect to u times the derivative of u with respect to x. Using similar steps from before, taking the derivative of this with the power rule gives us negative 1/4 because the negative 1/2 comes down, and we subtract an exponent, and when you subtract 1, you get negative 3/2. Derivative of u with respect to x is 2x plus 6. And now we can write this all kind of a little nicer. Negative 1/4 times u, which we said was x squared, plus 6x minus 1 to the negative 3/2 times 2x plus 6. And we could clean it up a little bit more as well by getting rid of the negative exponent. To do that, we'll put 1/4 like this. This has a negative exponent, so it goes to the denominator. This does not have a negative exponent, so it stays in the numerator. And then we usually don't write the 1. As a quick reminder, why did I get rid of the negative exponent here, but I did not get rid of the negative exponent here? It's because we're going to be done after the second derivative. If I know we're taking another derivative, leaving it in terms of a negative exponent is going to be easier. If I don't know about second derivatives or not, If I know we're going to be done, we don't need to take any more derivatives, it's much nicer to look at it this way. Great, so that's the derivative of h with respect to x. That's h prime. Well, g and g prime are much easier, right? G prime of x is just 2. G is just a line. Its derivative is just 2. So let's finish the problem. We got h prime, which is that monster. Times g, which is 2x plus 6, plus h, which is this guy, 1/2. Oh, we can rewrite this one, right? 1 divided by 2 times the square root of x squared plus 6x minus 1 times g prime. We said g prime was just 2. And now this actually does clean up a little bit. Notice over here, we have this times that. We can think of this fraction as dividing by 1. That's 2x plus 6 squared over 4 times this thing. And the second one's even nicer. The 2's cancel. And there are some ways that we could rewrite this to make it maybe look a little nicer. But this is good enough. This is our second derivative. Again, you are not expected to calculate that in this class. But if you're curious about what a messier second derivative looks like, there you go. This is a good time to thank yourself for signing up to business calculus. Otherwise, you'd be doing many, many, many of these probably. But yeah, for purposes of this class, we're not going to be taking second derivatives of functions this messy usually. Or if we do, in reality, like we just use technology or something like that. The important thing is that you know what a second derivative is You know what concavity looks like and know how to use it because we have application sections coming up. Let me know if you have any questions about this. Again, I purposely tried to pick some messier problems, give you some practice, show you how things are done. Whenever you have messier derivatives, the most important thing is just take it in small steps. Break it down into smaller pieces. And when you break it down into smaller pieces, things get a lot more manageable, even if the end result is still really messy. I believe in you. Thanks for sticking it out. Have a good rest of your day. Bye-bye.